Hello, everyone. My name is Wenlei. Today, I will talk about our project, Triton Distributed, which is a compiler that helps you programming overlapping kernels on distributed AI systems. And this work is done by many people in Triton C. So the outline will look like this. We will first go over some of the background, and then we will touch base on some key component within Triton Distributed compiler. And lastly, we will see some experiment result. So with the development of the large language models, distributed training and inference have become the key part, and there are various parallel strategies that have proposed to accelerate the training and inference, such as tensor parallelism, expert parallelism. And the best parallel strategy may be to achieve a great MFU is often mixed usage of all of them. And for large language model training and inference, there's need for a massive number of GPU. So even a marginal improvement in MFU can bring significant cost savings. So this is why we are focusing on the time that's spent on the computation part during the training and inference. So according to our previous study, that communication can account for ranging from 20% up to 80%, depends on different hardware of the total runtime. So eliminating this communication overhead has become a key point in improving the overall MFU. So today, we will focus on the overlapping optimization. And the example on the right showing that in the case of Alligator and Jim, we can use some techniques to allow them to run in parallel. Thus, this could reduce the overall latency and improve the MFU. So there are basically two kinds of approaches to achieve this overlapping. And the first one is called decomposition, where basically you can split computation and communications and onto multi-stream. And these computation and communication are often independent. So the second approach is basically relying on redesigning the kernel to fuse communication and computation together and allowing for optimal allocation of GPU resources. And these two approaches have their own advantage and disadvantages. The multi-stream one is kind of easy to implement, but the optimal performance is often limited. And the fusion method is often very hard to implement. So the challenge for distributed programming is focused on the memory hierarchy strategy. And so for single device, we have the register, cache, shared memory, and HBM to program. And there are two actual memory hierarchy to program for distributed scenarios. There are scale up and scale out remote memory. So for scale up, user need to take care of the long latency of the remote memory access and also the P2P data transfer between GPUs. On the other hand, modern GPUs have the NVLink Sharp, which provide on-switch reduction and broadcasting, these modern features for accelerations. And so these are called multi-mem operations that need to be used wisely to improve the overall performance. And similarly, for scale out, so programmer need to deal with the internal communication through NIC. All of this extra memory hierarchy increase the difficulty to program and optimize the whole systems. And nowadays, the current GPU programming status, for single device, we have the CUDA and we have CALAS, SIMT programming model, and some template-based programming patterns, which are targeting at professional GPU programmers. However, Triton did a great job on simplifying the programming model into a SIMT mode and also make it a Pythonic way. And similarly, for Triton Distributed, we adapt a programming model for distributed environment. We mainly target at ordinary users who kind of familiar with Python programming can directly use Triton and Triton Distributed. So power users who are experts in low-level programming, as we can see previous presentations, may also use our compiler to kind of reduce the development cost and without hurting the performance. So here we can see the overall compiler stack for Triton Distributed, showing in the figure. Users can program computation and communication parts in Python. And the communication part implemented with OpenShared memory primitives will further lowered into LVIR together with a BigCode library. The computation part will go through the original Triton stack to lower to LVIR. And finally, PTX or GCN are generated and activated on the target accelerators. And note that we conceptually separate the communication and computation part, but in real life, they have interactions. So for example, in a computation kernel, you may want to issue some of the communication, or you may want to wait for some data transfer from other GPU. Right, so this achieved through the data or signals, and we will detail later. Here is a program model that adopted by Triton Distributed. Our program model follows the MPMD model, which is multi-programs or multiple data. The MPMD models allow the computation and communication task to run parallel and cooperate with each other to complete a global task. The core of our program model including a couple of concepts. The first one is called symmetric memory. So basically each rank, each GPU, for example, allocate a memory buffer in a global scope with the same size, and each memory buffer has a separate memory address space. So there's no uniform virtual address space from global view. And the remote memory buffers cannot be accessed directly through pointers. It has to be achieved through some specific primitives, as we will see later. And the second one is the signal exchange. So operations on each rank can use signals to communicate with each other in a consistent way. A signal basically is a data object which in the symmetric memory. And for the signal, there are kind of a couple of operations on top of the signal. Basically, you can set the value, you can clear the value, you can change the value for your own purpose to achieve some of the operations, such as a spin lock waiting for some data to arrive. And now, next is async task. Operations such as data transfer and computations are treated as async tasks and could run in parallel. And async tasks can be synchronized through signals. And so for different hardware backends, so there are different ways to implement this async task. And for GPU, you can do multi-streaming and multi-threading. So multi-streaming, so basically rely on runtime task queue. And multi-threading, you can leverage parallel hardware units. And for example, in the figure, we demonstrate the above concept. In this example, we have two nodes, and each of them has two GPU. And the upper part of the figure shows the symmetric memory in green, symmetric buffer. And each rank and signal exchange between this within a rank here or across a rank. You can see the signals are used to communicate between this, interact with communication and computation. In the lower part, we use a timeline to show that on each rank, there are 3 tasks running in parallel. There are internode P2P, and there are intranode P2P, as well as computation. Tasks at different ranks also run in parallel, and each rank will launch this task simultaneously. So the computation task, as you see here, is basically is a single kernel run on the device, but the order of the tails of the computation is carefully tuned to minimize the waiting time for the communication, and we will see example later. So besides this, in the real world training and inference, so developer also has to deal with the resource partition. So basically, you have to deal with the different kernels. Will either use SM, and they also could compete in bandwidth for communication kernels. So here's a summarize of the communication primitives in the table. There are mainly 2 categories, the open share memory one and non-open share memory one. So the open share memory primitive will basically will be translated into different implementations on GPUs, for example, NV share memory or ROG share memory. And the non-open share memory primitives, on the other hand, provide different hardware-specific operations, such as atomic ones or multi-mem operations. And also worth to mention is that open share memory primitives is not only limited to GPUs, other NPUs can also adopt the concept. So here is an example that written in Triton distributed. This is an internal all-gather gym. And we can see three parts: the communication part on the left, which is a producer all-gather, and the computation part of the consumer gym on the right top, and the whole side on the right bottom. So the communication part, we assign different tasks to different thread blocks, and part of them are responsible for the internode dispatch, and the other are for the internode data transfer. So these two groups are designed to run in parallel so that they can overlap with each other. And for the computation part on the right, so it's basically the original Triton gym kernel, but with some minor difference is that there are actually two primitives. The first one is called wait. It's basically the wait will produce a token related to a signal. And the second primitive, consume token, actually take the token and create data dependencies between the token and its following data load. So different tiles in gym kernel will run in parallel, and each tile will wait for its own signal and overlapping its with its dependent communication and other tiles computation. So finally, the host side code, basically it deals with symmetric memories, allocation, and launching with the different streams operations. So to achieving like the optimal performance, it often requires careful design of the communication and its integration with computation. So here, let's divide into some optimization details. One critical thing, as you can see on this slide, is to choosing between push mode or pull mode for data transfer, basically for P2P. So push mode, that basically you send local data to remote buffers and also set some remote signals. And after push operations, global barrier is often required to ensure that different ranks have all the data. So this mode is simpler, but it's not guaranteed the data arriving order, especially on GPUs. And for the pull mode, basically we are fetching the data from remote buffer to local and set the local signals. This approach requires extra barrier before and after communication to ensure the data visibility and completion of the data transfer. The advantage is that this one, you can expect the precise control of the data arriving order. However, so it has the extra barrier, so it has extra overhead. So here in this slide, we show the low latency communication altogether for small message scenarios. So basically here we use like non-open shared memory primitive for the intranode broadcast, which is the multi-mem operation. And we use a low latency protocol for internode data transfer. In detail, the multi-mem primitive is to do the NVLink broadcasting. And this is the PTX instruction set and to store the data to all the ranks that has a very small overhead. And for internode communication, we apply the RL protocol, which we have to pack the data with the flag into a 8-byte data chunk and to send them entirely to the remote rank. So this protocol is fast, but it kind of wastes some memory because it's you have the flags. And this is very suitable for small message scenarios, but not for large message scenarios. And for this slide, it's still about optimizing communication. And for this case, is a internode gym reduced scatter. And it basically needs a couple of parts, naming like internode scatter, local reduction, and internode P2P communication. So here we show a case that we do a very precise resource partition between different operations. So first you can see a gym producer kernel, which consumes only partial of the total SM for this NVGPUs. And to optimize the usage and communication efficiency, we employ an overlapping strategy that for internode and internode communications. And for the internode, we use another stream, and it's only use the copy engine without consuming any of the SM. And for the local reduction, we have to use SM to do this computation. And to make sure that this reduction kernel doesn't consume too much SM, that it will affect the gym performance. So we test it out and we use only 16 SM for this reduction. And for the later, the cross-node P2P, you only use 1 SM to do the internode communication. And finally, you have the local reduction to get a final result at all SMs. So it's very precise to control the different resources for different kernels on different streams to reach a good performance for this case. And here's another optimization case for different hardware which has different interconnect. And for example, NVIDIA GPU has NVIDIA topology, where each P2P can consume the full bandwidth. But for AMD, which has adopted a full mesh topology, to have a relatively good bandwidth, you have to make sure you use every link between GPUs, which means all of the XGMI links, to achieve a relatively good bandwidth. And besides, different number of copy engines are existing on GPUs, and so depends on use cases, you may want to use this copy engine as well precisely to achieve a good bandwidth, as we showed in the last slide example. So here is the part where we're optimizing the computations. So the computations had to be accommodated for the communication order. So here is basically about the swizzling, meaning the computation order. So for all-gather chain on NVIDIA GPUs, we show the swizzling order on the right-hand side, and we use only 4 ranks for demo for this case. At the very beginning, each rank will occupy a chunk of data. So for the first step, each of the GPU will use its own local data to do the computation. And at the same time, each rank will gather the next chunk of data from another GPU. And then the second step, it will reuse the step 1 data to do the computation, and at the same time to gather data. However, on AMD GPU, the swizzling design is a bit of difference because of the interconnect, as we just saw in last slide. So if we only gather next chunk of data from another GPU at one time, then the maximum bandwidth will be limited. So we are not fully using all the XGMI links. So to fully use the bandwidth, we have to, each rank has to be gathered data from all of the other GPUs at each step. So we have to further tell the chunk data into subchunks. Then for the, so which showing the lower part of the figure. So on step 1, it gathers the first subchunk for all the other ranks and do the computations. And following the other step, will follow the same pattern. So here is this slide. We want to show the classic auto-tuning part. So we have been seeing quite a number of different optimizations, and the optimal combination of all these techniques are kind of depends on different scenarios. So we apply a auto-tuning but in a distributed way to tune all the optimization knobs. So our auto-tuner actually accepts a target function that including all the communications, computations, as well as some whole side logic. So the target function is executed as a whole, and the profiling steps will be carried out progressively. And finally, upon completion, so there will be some synchronization operations to aggregate the tuning information from all of the devices, and thereby we're selecting a global optimal one for the best configurations. So here is basically a summarizing of all of the optimizations in this table. And what here I want to mention more than overlapping is that beside overlapping kernels, we also provide a communication patterns in Triton distributed. For example, we have some customized P2P communications, where here we have a more precise control on how many SMs you can use, and we can achieve a similar performance as Nico, but only consume less number of SMs. We also have the low latency EP auto-all kernel. We call it like dispatch and combine. We can reach on-par performance with DPP, but only for partial of the EP settings. So the difference is basically the IBRC versus IBGDA. And the IBGDA support is still in progress. And we also have some study that the SM numbers and the Q pair count actually also matter for these communications. And more importantly, we only achieved use hundreds of lines of Python code compared to DPP, where there's thousands of lines of CUDA code. So here is a new feature that I want to introduce, the MegaKernel. which we want to kind of use the forward pass computation and communication as a single big Triton kernel. And we want to further eliminating the kernel launching overhead, further increase the utilization, and more importantly, this will be in Triton level, not in the CUDA level. So the design of the MegaKernel stack in this Triton distributed is in two parts. We have the compile time and we have the runtime. So at the compile time, so build task will break in the operators into many different tasks, and in Triton, we often view a tile or block as a task, which will finally map into SMs. So tasks that belong to the same operators, it's kind of similar to each other. For example, in MetMod, tasks are different tiles during processing, and the difference only the location or the tile ID within the program. And for the optimizer part, once we have the different tasks, we need to deal with their ordering or their dependencies. Their dependencies the operator dependency will convert into task dependencies. And every task can start its own computation once the dependency is satisfied. So we use a scoreboard tensor to check them. And scoreboard can release the task, can wait for some tasks to finish. And next is the scheduler. So tasks need to be assigned to different SM for execution finally. And the different strategy can be applied for this scheduler is that it can be simplified the round-robin fashion or some other swindling pattern. So every SM will maintain a work queue to process all the tasks. And in the code generation step, basically all of the tasks in the queue will generate a huge Triton kernel with some dispatching logic to dispatching for different tasks. And at the runtime, it will just decode and run it. So let's take a look at the experiment result. So here we first have the kernel level evaluation. For the intra-kernel performance on MegaGPUs, for altogether GEM, we can reach 1.4x speed up compared to PyTorch Nickel. And for GEM reduced scatter, we can reach roughly 1.3 compared to Nickel. And we can similarly on AMD GPUs, we reach about 1.1x speed up for altogether and GEM reduced scatter. And we also have the internode communication kernel, fusion kernel. And for this case, we can reach up like 1.3x for altogether and 1.4x for GEM reduced scatter. And note there are many more patterns in our report, and please take the details in the report. So here we show another pattern which are more popular. So it is a GEM or reduced. For this pattern on NVIDIA GPUs, we can reach 1.5x speed up compared to PyTorch plus Nickel. And each bar within this figure is kind of represent a different problem size. And then for end-to-end evaluation, we have these settings. We basically use Tianwen different side models and also use seed open source models. And we apply two strategies for the tensor parallel. We apply the split version, altogether GEM reduced scatter, and also the GEM or reduced pattern. And for layer-wise, we have the module implementation, TP attention, and TP MLP. And for the full model integration, we apply the CUDA graph optimization. So here's a brief summary of the end-to-end evaluation for Tianwen models. For end-to-end, we can briefly reach a 1.3x speed up compared to the PyTorch. And for seed models, similarly, we can reach 1.3x speed up for both decoding, for both prefill and decode. And for last slide, I want to show is the MegaKernel performance. And for this case, our MegaKernel in Triton distributed can reach even up to 1.8x speed up compared to the basic version, which is PyTorch plus the CUDA graph. So the take-home message, so programming overlapping kernels as well as distributed system is easier than you think, and so just try distributed Triton. And yeah, thank you. That's all.
Thanks for the presentation. I have a question. I know like for ByteDance, last year they released the flux operator, which also emphasize on overlapping communication and compute. And how is the performance compared with these two? And also like in ByteDance internally, how is everybody switching over from manually writing operators versus like using Triton to do the auto-tuning and using compiler strategy?
Actually, that is a great question. And actually, we have some performance comparison for Flux. So basically, we are the same part of people that are doing Flux and also distribute Triton. And the trade-off is that in Flux, we have to program in kernels. So we have to modify a lot of part of the kernels. And to be honest, it's not very easy to iterate and modify a lot of part of kernels. So basically, it takes us a lot of time to write a Flux kernel. But you can have almost all the control of that. But the iteration time on Flux kernel is basically too high. So we are kind of suffering, like for example, multiple days to write a new Flux pattern. So that's part of the reason that we switched to Triton distributed. As you can see, the performance, basically Triton distributed can reach on-par performance or even better for some of cases compared to Flux kernels. And for some cases where it can reach better performance, the reason is because in Triton distributed, we can easily try out different optimization patterns. As you just see the previous slide, you have different streams on using copy engine and the SM margin. But on kernels, to be honest, it's very hard to try out many of different optimization to achieve the on-par. So the real difference is actually the iteration time. So the Triton distributed grant us some flexibility on quickly iterate different optimization strategies. That way we can try out different optimizations, and some of the cases may have better performance compared to original Flux patterns.
Yeah, thank you.
Thanks.
Thank you for the talk. I just had a question. So I know that in the original implementation, you guys use static tile swizzling and the compile time auto-tuner. I'm curious, did you guys ever do any like testing internally about making these dynamic at runtime or doing like real-time retiling strategies? Like, is there any effort there?
That is really a good part of the question, and that I guess part of that related probably the MegaKernel. In the MegaKernel, we want to try some more optimizations, as you mentioned, some dynamic ways. But I would say it's still a currently ongoing effort.
Okay, and,
yeah.
and in particular, like I'm just curious, as a little bit as a follow-up, if you were able to make this adaptive or this retiling strategy at runtime, it should be suitable for multi-GPU heterogeneous hardware by default, right? That's the main advantage. At least I can see why it's a worthwhile effort, right?
Yeah.
Okay, thanks.
Okay.
Sorry.
Hey, thanks for the talk. So I was wondering whether the primitives that you have added to Triton, how do they interact with the existing optimizations in Triton, like pipelining? Did you have to disable some optimizations that Triton itself does, like pipelining and that kind of stuff to obtain results, or did you have to modify those passes to add support for these operations?
Yeah, okay, that is very good, like detailed questions. So that kind of relate to the optimization strategies when you optimize the overlapping kernels. First, you may want to have a good implementation of the computation itself. For that case, we will try out different version of the gem. For example, we have different, either you want to use TMA or use persistent, and it actually depends. It depends on many factors. As you can see previous example, for cases that you really want to do a persistent kernel because you want to do the resource partition, you want to do the SM margin, right? Your computation kernel, for example, gem, only can consume a partial of the SM. Then in this case, the other communications can use the rest of the SM to do the communication in some of the cases. Because you cannot always use to count on the copy engine because the long-term overhead is kind of large. And especially in an inference scenario, you probably want to use SM to do the copy. So basically, there's no easy answer. So it kind of really depends on the user scenarios, depend on your cases, depend on your workload, and it's a kind of complicated process.
Okay, and just a follow-up question. So for the MegaKernel, like, so what was it a manually written Triton kernel, like for the that corresponds to the ML model, or like how did you, I guess, come from the ML model to the Triton kernel?
Yeah, that's also a good question. So for we trying to reduce effort to re-implement the Triton kernel, but right now for the Triton MegaKernel to work, it just a framework, right? It has the compile time, runtime. It basically code gen a huge Triton kernel. It dispatch the task into the Triton kernel itself. So basically you have to, if you don't have that Triton kernel, you have to re-implement yourself, and for different models, right? But we are trying to reduce the effort to have some patterns that users don't have to rewrite themselves and to use MegaKernel.
Okay, thank you.
We're actually out of time, so sorry about that. Thank you very much, Wenlei. Let's thank Wenlei for a great talk.